Good.
So, for those of you who don't know me, my name is Marina Silva. I'm a marketing supervisor.
And I'm Henry Smith. I'm the engineering services supervisor.
And today we are going to talk to you about HVAC maintenance. So we'll start by looking at the problems that industrial and commercial HVAC units face, review alternative repair options, look at methods of how these solutions can be applied, and see some case studies. And you're also welcome to type your questions throughout the webinar, and we will answer them all at the end.
So you guys might be thinking, like, why is HVAC, or heating, ventilation and air conditioning, such a hot topic currently? As we know, whether it's a commercial or an industrial facility, HVAC systems need to be in operation almost 24/7. Industrial systems use it to change the temperature of certain fluids or gases in order to keep the process going, and commercial units use it to keep a building's occupants either cold or warm. So therefore, it's really important to make sure that these units are in working order. Disruption shouldn't really be prolonged, as it can normally increase your costs and prevent work from being completed in the first place. So even if an industrial site doesn't have something big like a heat exchanger, there's usually an aircon system or a heating system or something like that involved. More so for the commercial side of things, these units are often out the way. So they'll be up on a roof, in a spare room, somewhere off to the side where they usually get forgotten about. And it's not until the day that they stop working that you remember that you need to have good maintenance routines to make sure that they're up and running all the time.
So let's look at some problem areas within an HVAC unit. So first we will look at condenser water systems, then chilled water systems, and finally review problem areas within air handling units and ductwork. HVAC is an almost entirely closed loop process, so the whole system needs to be functioning in order for any output to be achieved.
The main thing that's really stopping this output from happening in a lot of cases is corrosion. As we all know, corrosion is a massive battle for anybody who owns any type of equipment usually. And building owners, managers, integrity engineers tend to struggle to maintain the integrity of units such as HVAC. So to get a corrosion cell, we only need three things. You need an anode, a cathode, and an electrolyte. But unfortunately, in this type of situation, all of these are present within an HVAC system. So to take an example, as you can see an example of a tube sheet heat exchanger on your slide at the moment. And they're a classic example of where you get this type of damage. Large surface area of metal in contact with a large volume of liquid makes them susceptible to corrosion. Not only the standard general corrosion, but also bimetallic or galvanic corrosion as well. So if it's not properly treated, effectively the metals gradually self-destruct when they're exposed to these circumstances. Usually in a tube sheet heat exchanger, the tubes are made from copper while the face is made from something like mild steel. And it's because copper is a more noble material, the steel begins to corrode preferentially, causing a really rapid loss of material. This becomes a problem the longer it goes on. If it's left completely unchecked, the wet and warm conditions inside the HVAC system, combined with any cleaning agents and process chemicals, accelerates the corrosion massively. So some of the standard solutions you might come across, in a lot of cases, replacement is normally the first port of call. Obviously, this brings you back to your starting point with a brand new bit of equipment. However, it doesn't necessarily last. So you need to ask yourself, have we found and fixed the root cause of this issue? If the answer is going to be no, then you can probably expect history to repeat itself. Patch repairs and weld overlay are, to put it simply, adding just more metal to the surface, and with these you can encounter a few issues. Either you're not fixing the issue permanently, it could happen again in some cases, or over time you'll need to complete multiple repairs to the same piece of equipment. So it makes sense to choose something which would prevent it from happening again across the entire piece of equipment. You could perhaps choose to use a certain type of paint or sacrificial anodes or something similar, but these either have a limited service life or require constant replacement and maintenance. So in order for them to be effective in the first place.
So we'll look at the condenser water systems now. Large office buildings, hospitals and schools typically use one or more cooling towers. And unlike the large concrete units we see at power stations, these smaller cooling towers commonly constructed from galvanized steel. And the combination of air, water, chemicals, and heat in cooling towers creates a severe corrosive environment. And we usually see perforations and severe metal loss on units which have been in service for some time. So let's look at some of the solutions that we can recommend for these types of problems. So our first case study brings us to a local bank where we are looking at 3 Marley cooling tower cold wells. And this type of system is usually protected by galvanization of the steel. However, the chemicals which were being used to treat the water were so strong, they actually ate away the galvanized sections of the steel. And the exposed area, which was the pans at the base of the unit, which we can clearly see in the pictures here, began to corrode, and they were concerned that a leak would develop. So the decision was made to coat the area and seal the gaps around them. And materials used for this job have excellent adhesion and do not corrode, so non-metallic materials that Belzona offers. So problem solved.
So the next example we're going to look at is an example of a part of the HVAC system, which again is forgotten about, but is part of all of them. So pipework. We focused a bit on the towers and the big units so far, but obviously something needs to transport all this water and all this liquid around the system. So as you can see from the picture, the geometry of this leaking pipe made it very, very difficult for them to come up with an effective repair. The engineers who were tasked with making a repair were actually really struggling to find something which was suitable to do the fix effectively. So Belzona 9611, the ES metal, was used initially to stem the leak, and this gave the engineers just enough time to fully wrap the small pipe section and create a more permanent repair. By comparison, in the traditional repair methods, so a cut and weld would have cost upwards of about £50,000 per hour just because they had to shut down the full system in order to effect it. Considering that this repair was inspected and found still be going strong 3 years afterwards, shows how much of a saving they did make on this application. In the rest of the system as well, so obviously we have the pipes, we have the bigger units, but the air that's been exhausted out of the system has to go somewhere. So normally you'll find fan blades within the system. On first glance, a fan rotating and forcing air out of the system doesn't seem like it would have that much damage done to it. However, much like their bigger turbine counterparts, the small amounts of moisture in the air can cause really severe erosion to the leading edge of the blades. The blades themselves are designed to a very, very tight specification, so any deviation in this design causes issues such as efficiency loss. The repair method itself is relatively straightforward. So begin with surface preparation and rebuilding using a paste grade. You can then apply a ceramic coating onto the leading edge to prevent that erosive damage from the moisture contained in the air, and then apply a general polymeric coating for protection from corrosion and also chemical attack to the remainder of the blades.
So you can see here a clear picture of exactly what happens when this erosion corrosion issue goes unnoticed for a very long time. So we see severe erosion on the FRP fan blade, and in terms of repair, after surface preparation and conditioning, the worn edge of the blade has been rebuilt with the ceramic epoxy that Henry talked about before, which adheres very well to FRP. Combined with the reinforcement tape, it will prevent blade disintegration and strengthen its structure. So it's a great alternative to replacement, and jobs like this can even be carried out in situ.
So the reason for this next repair taking place over in Texas was because the system itself was beginning to lose efficiency, mainly due to the erosion of the blades. The customer was finding that they needed to replace the blades every 5 to 7 years, and because they had 12 towers, you can imagine in each of these towers they have a couple of blades. That's going to get very, very costly for them to constantly replace them. So using 4 different products from Belzona, including 1111 and some of the ceramic coatings, they rebuilt the blades back to their original specification. The customer actually noted after that they'd saved as much as 80% on their replacement costs. This was down to the minimal amount of material and equipment they needed to do the repair, and also the overall cost of buying new blades in was very high in comparison to the repair that they completed. So we're going to have a quick look now at the chilled water system section. So chillers and heat exchangers are a vital part of any heating or air conditioning system, and failure can normally be caused by a couple of issues. So as we've already mentioned, corrosion leads to wastage and metal loss on the tube sheet face around the coolant tubes, and this can be classed as either general or galvanic corrosion. And the second one is leakage. So this loss of metal, mainly through erosion or corrosion, can cause leakage of this coolant and potentially contamination of the chilled water itself. Again, drops the efficiency. Normally, a corrosion allowance is designed into the system to accept anticipated levels of metal loss. However, throughout its lifetime, metal losses will gradually occur, and if the corrosion allowance is exceeded, and the gaps begin to appear, eventually you'll get recirculation, which again drops your efficiency massively. So in order to prevent this from happening, there's a way to apply epoxy materials to a tube sheet face in order to stop the corrosion from the start. So first, an epoxy paste is used to rebuild any lost metal, and then we use a ceramic-based coating to prevent the damage from reoccurring. If you can prevent that liquid from contacting the surface in the first place, then you can prevent the corrosion from even beginning.
So let's look more closely at the process of repairing and protecting tube sheets. Yeah.
Okay, so this is just a quick example of an application we did onto a chiller, a tube sheet application. So the first step is always surface preparation. So the first thing they're going to do is insert these corks into the tube sheet. And what this does is it blocks up the tubes themselves. And the whole reason we do that is because we don't want any of the grit from the grit blasting. We don't want any product going down the tubes because it would block it. And a blocked tube would again reduce the operation of the operational efficiency of the system. So once all your tubes are in and your corks are in and everything's enclosed off and ready for blasting, you start with surface preparation. Ideally, grit blasting is the preferred option for it because it removes all the corrosion, it cleans the surface really well, and we're looking for a 75 micron profile to the surface. Afterwards, remove those corks and replace them because they would have been slightly damaged from the surface prep process, and again refasten the corks back into the tube sheet itself. In order to get this metal back up to a surface where we can apply a coating, you then mix up the epoxy paste grade, and then he's just going to use a spatula and paste that onto the surface after the surface prep to rebuild it and get a nice flush finish to the application. After the Belzona is cured, the paste grade is cured, you then remove all of the corks in order to avoid again to avoid the product going down the tubes, replace them if necessary, and then you can apply the Belzona 1321 or other ceramic-based coating directly on top of the Belzona paste grade, as long as you're still within that overcoating window. They used Belzona 1121 in this example because it had an extended working life and also an extended overcoating window for the product, which meant they had plenty of time to apply this material on top. Once both of them have cured, you can then remove the corks finally from the system and dress back the coating to give you a nice flush finish where you've prevented the liquid from contacting the surface, and you've also isolated the tubes from the tube sheet face, which means you've prevented any type of corrosion from happening in the future.
Great, thank you, Henry. We do also tend to get a lot of questions about how you can remove the corks.
Mm-hmm.
So
in terms of removing the corks, if you're going to be, you can do it manually using a corkscrew. It takes a bit of time. It's quite labor intensive, but it is the easiest way to make it most accurate. Or if you can get to the other end of one of the tubes, you can use some compressed air and you can blow the compressed air down the tube and it will pop the cork out on the other side. That's the easiest way I've found to remove them myself.
Great, thank you. So before I talk a little bit more about this application, question for the audience. Can you guess how long this repair has been in service? So it's, and if you can guess, please type your answers in the chat, please. So how many years this tube sheet repair has lasted? And this heat exchanger, we unfortunately don't have a picture of the before state. So this is the picture of after X amount of years in service. So it's been suffering from galvanic corrosion, and the customer was quoted $350,000 to replace this unit. And we're not even talking about the cost of downtime here. This is just the cost of the new tube sheet. So a Belzona repair was completed for approximately $25,000. So you can do the math. And the application itself, so we have a few guesses, 10, 7, 15. It does depend on the situation. What we tend to see is that once the tube sheet has been repaired, it will last for a very, very long time because you eliminate the problem. So you eliminate the problem and it will last until you retire it. So in this case, the application was completed in 1973 and the unit was set for retirement in 2009. So that happened 35 years after it was originally repaired. So it's a bit of a testament to the longevity of non-metallic materials.
Yeah, so similar sort of vein to the previous one that Marina was just talking about, but this was more of a commercial type application because it was in an airport actually in Stockholm in Sweden. In some cases, the cooling water that's used within the heat exchangers isn't necessarily brought from a pure water source. So the water supplied to this heat exchanger actually came from a local river system, which meant it came with the water, but also lots of other undesirables within the system. Mainly, the thing they didn't filter out was the salt. And obviously, as we know from marine environments, corrosion accelerates massively when there's salt involved. The chiller itself was steam cleaned and all those salts removed, and then they followed exactly the same process as you saw in the video a minute ago. They repaired it in 2005, came back and inspected it in 2008 and found it to be in exactly the same condition as it was when the guys reassembled it back after they'd coated the system. And then again, a similar sort of system, but a bit smaller this time. The chiller unit in this case was over in Indianapolis. It was in a downtown area, which is important for the application. It became corroded over time because of the heat generated in the system. A poor weld seam had actually caused some of the condensated water to pool between the two layers of insulation, and that resulted in a lot of CUI or corrosion under insulation damage to the metal wall, which caused it to really thin down a lot. The biggest problem faced by the engineers was that replacement would be incredibly expensive, mainly because they needed a huge crane to get this out of the building, and it was in such a densely populated area that it would be almost impossible to do so. The Belzona repair itself was completed with no downtime whatsoever. The system could be running while they completed it, and it prevented the issue from reoccurring, meaning that they could use the repair on similar equipment and effectively just forget about the issue after they've repaired it. So now if we move on to the final section, so obviously the air handling system suffers many similar problems as the pipework. Corrosion, internal corrosion due to the water condensation, higher temperatures as this handles a lot of the exhaust air from the HVAC system, aggressive cleaning chemicals contained within the condensate, and even sometimes microbiological growth within the system. Obviously, the ductwork itself is similar to the pipework for carrying the water, but it's more for the air side of things, and it's the lifeblood of the air-based system. So just like the pipework, problems come with the design. Normally, there's a lot of junctions, seams, seals, joints, and other different crazy geometries in there, and this gives more areas which are susceptible to leaks. The failure of the joints and seams can also allow critical ingress of water and the disruption of the airflow, and it affects the cooling and the heating process. Belzona's flexible repair materials can restore these joints and seams as a long-lasting solution. Sealing at the interface between where the roof and the ductwork meet can also be achieved with these same Belzona flexible membranes, and the complex contours themselves are quite difficult to coat. So a system which can cope with being applied at various angles is always a positive. Again, these Belzona materials can be used for protecting both the internal and the external of the ductwork, as well as T-pieces, elbows, and other difficult to coat areas.
So as Henry was talking about the versatility and flexibility of Belzona materials, let's look at these features in action. So here, the effect of weather and UV caused rubber seals around ductwork penetrations to degrade, allowing rainwater to leak directly into the production area, creating disruption in production and, of course, safety issues. So the joints were resealed with an elastomer before applying a fully reinforced flexible membrane system. And the application was completed in 2 days without disrupting production, given a long-term water and weather-resistant solution. And here we are looking at cooled air rooftop ducts at an Ivy League medical school. Urethane insulation and mastic were no longer watertight, as you can see in the top left picture there. Insulation was wet and water was leaking into the building. CUI was feared as well. So the original plan was to remove all wet existing insulation, re-insulate and waterproof over 200 feet of 60-inch carbon steel ducts. Very expensive, a very labor-intensive exercise. Thanks to, Belzona came up with a better solution. Due to its membrane being microporous, there was no need to remove the insulation, and this membrane could be applied on top of the existing system and is still in excellent condition after 3 years in service.
So this is our final know-how in action. This was actually, again, another bit which people tend to forget about. So we've got these big fans inside our HVAC system, and what's driving the fans? Well, it's the shaft. In this case, the bearings on the shaft actually failed and seized, and that caused it to score and take out a huge section of the shaft themselves. So they had to cut this back, as you can see in the top left picture, remove all the damaged material, and then they needed a solution to be able to reform this and have it back up and running the following morning. So this repair was done overnight. They used Belzona 1111 and a former, as you can see in the bottom left picture, to give them a good solid finish and a good clean finish. So when they removed it, there's minimal dressing down and they can put the shaft straight back into service as soon as it had cured. There was no need to machine it or grind it afterwards, and there's nothing additional that needs to be added to the system in order for it to be ready to be to put back into service the following morning.
So just to recap, we wanted to summarize some of the benefits of using non-metallic and other Belzona materials for HVAC repairs and protection. So cold curing and solvent-free nature of these materials not only makes them safer to use, but aids the application as there is no shrinkage or distortion of the material during curing. And all cure with a wide application window and no external heat or specialist tools required.
And in terms of performance, all the materials we've shown have got or exhibit very, very good adhesion to a wide variety of substrates. And there's a lot of products which can cope with a lot of varying levels of chemical or mechanical attack. Obviously, we don't have time to go through every single one of them at the moment. And these products are also designed to provide a long-term solution as opposed to just a quick fix. So you saw the example of the heat exchanger that lasted for 35 years. That's a considerably long time if you take into account all the different replacements and all the different weld jobs that they might have had to done should they have not used the Belzona system.
So as you've noticed, we've mentioned a few case studies, and we just wanted to, well, either tell you about it if you don't know, or remind you that we have a website where we actually share all of the case studies that we have collected from around the globe, and you can find it on khia.belzona.com. Very simple to use, similar to Google or any other search engine. You just search for, I don't know, tube sheet repair or heat exchanger, and you would find all the different repairs that have been carried out. Some of them have been inspected after years in service as well. That's where we got the 35-year example. And another benefit of using Belzona systems that we can talk about is our technical know-how and support available across the globe. So Belzona has been working with a large network of distributors for many, many years who are very experienced in the application of such materials, and they can offer local service and support. And if any solutions during this webinar have caught your eye, Belzona will be able to assist you wherever you are. And to find your local representative, you can visit belzona.com. So thank you for joining us today. You will all receive a link to the recording of this webinar at the end of the day, and the transcript will also be added on our blog, blog.belzona.com. Henry will now answer any questions you may have. So you're welcome to type them in the chat or use the Ask a Question feature. Maybe we'll start by addressing some feedback we've received. Mm-hmm. Maybe look at Daniel's solution to cork removal.
Yeah, so Daniel's suggestion is you effectively buy a bottle opener and then you cut and throw away the mechanism and just keep the screw on the end of it, which is, yeah, that's a fairly straightforward way of doing it. You could go for the handheld version, but obviously it would take much, much longer. So it's a good engineering solution to get around being able to, that'd be more for where maybe you can't access the other side of the tubes to push the compressed air through, or maybe the tubes are so long, or it's one of the systems where it loops back on itself. You can't force enough air through to get the corks out. So yeah, it's a very good solution to a fairly simple problem, I guess.
And it saves time.
It does, yeah. It saves a lot of time. Yeah.
So yes, Daniel, please do send us pictures. So a few people commented on the fact that it all depends on the situation when you are repairing a heat exchanger, for example.
Yeah, there might be some cases where it operates at an incredibly high temperature, in which case the non-metallic alternative, such as Belzona, may not be suitable. For a wide variety of applications, then yeah, you could use Belzona, but it depends, like you say, on the upset conditions, abnormalities. So maybe there's a big temperature spike, or they put a really, really nasty chemical through the system every week. So again, it's really important that you get a full list of everything that might happen with the system. Even if it doesn't happen, it's better to know and plan for it than it is to find out 2 years later that your Belzona or your repair has stopped working because of something that was missed at the initial stages. So yeah, having that list of conditions that you expect is key in making sure you spec the correct material for the type of repair that you're doing.
Excellent, thank you. So does anybody else have any questions or comments?
All right.
Well, maybe we've covered it all very well. Oh, there we go. Just a question from Saeed. The highest temperature that Belzona products can tolerate? The
highest temperature product coating-wise that we have goes to about 160 Celsius, and that's Belzona 1593. Normally, that's not used in a lot of the applications we see with heat exchangers, HVAC systems. It's usually down the lower end, so we're talking less than 100 degrees. But yeah, 160 C is the highest we recommend our, thank you for the, yeah, so 160 C, sorry, is 320 Fahrenheit approximately. And that's the highest temperature for immersion circumstances. If it was dry, so you had air in the duct work as opposed to a liquid in the piping system or the heat exchangers, then we can potentially push that a bit higher. But generally, that's the highest we tend to go to with our products.
Yeah, and what's the highest for dry heat? 200 and...
Highest for dry heat, as part of engineering, I'd recommend about 200 as a maximum. I wouldn't generally go any higher than that. Again, it's case by case. So if you have something where maybe it goes to 205 and it's not particularly aggressive, then you can quite easily give us the information, or we can help you select the correct product for it.
Great, thank you, Henry. Another question from Ottavio. What is the temperature work range for 3100 series? Yeah, so 3100 series are designed for environmental conditions. So outdoor temperatures, obviously in the UK, it's pretty much freezing most of the year round. Probably about 10 degrees is our average. Middle East, Far East, some places in the US, South America, they'll get a lot hotter, obviously. So 50, 60 degrees, I'd say probably 60 degrees centigrade is probably our top level. But the products themselves are designed so they can go ever so slightly higher. So if it occasionally sees a jump to 70 or so, you might find that, yeah, the product will be okay, but that can only be for a short time. So yeah, I'd say ambient, like global temperatures is what the product's specifically designed for, not like an in-service heated environment. No problem. Okay. Thank you, Henry. Right, well, thank you all very much for listening to us today.